Friends, hello again. Extremely happy, as you can see, to do these lectures, mini lectures. I'm going to try to explain power laws, the Pareto distribution, very quickly, and put it in perspective with other classes of distribution, namely the three main ones. I'll present in a minute. But let me tell you why it's very intuitive and very well known. A lot of people associate power laws with the 80-20 law, principle, guideline, whatever you want. 80% of the people in Italy own 20% of the land, and 20% of the land own 80%. Sorry, 20% of people own 80% of the land. So that is how it was born with the work of Pareto, Vilfredo Pareto. It is fractal. We'll see what fractal means. Fractal in the sense that you can recurse. These 20 also have an 80-20. You apply it to them. You do it again, the last 20. You do an 80-20 on them until you get to about 50 or 1. So 50% of the land is owned by 1% of the people, compatible with that, if you have the same proportion being preserved. And we'll see how these get preserved with the notion of power law and power law decline of the tail of the distribution. So one mention, as I said, of the class of distribution. Okay, now you have a class of distributions. This is going to be, we have mainly three classes. The first one, I would call it Gaussian. It's not really Gaussian, but the distribution under summation, as we saw with the law of large number, with the central limit theorem, things converge to the Gaussian rather rapidly. Within the Gaussian, of course, we have the lower, I would call it the lower Gaussian, like binomial, and upper Gaussian is a Gaussian proper. Okay, because the binomial doesn't go to infinity. These are finite, infinite support delivers on plus infinity, minus infinity. That's just, this goes on finite support. And below the binomial, you have the Bernoulli. And of course, below the Bernoulli, you have the so-called degenerate distribution. So this is the Gaussian. In these classes of distribution, you can do a lot of statistical inference. Your safe thing of a summation, when you have a large sample, the average of that sample will be summed. You converge, everybody's happy. So, sorry if you're not seeing very well here. Let me raise the board a little. Okay. Second class, let's call this class sub-exponential. Sub-exponential. Okay. And of course, we draw the line here between two classes, power laws, and let's call it the sub-exponential, but not power law. Okay, we won't give it a name. In here you rank them log normal, nasty distribution. Below log normal, say we have the exponential Laplace. In between, maybe you have the gamma, which is okay. I mean, they're all related with parameterization or mild transformation, and then you have a bunch of things. This is, let's call the semi-fat-tailed, thick-tailed, but not power laws. Now, within power laws, you have Pareto distribution, the Pareto distribution, or distribution with Pareto tails, student T, or something more general, the stable distribution. Within here, you have the Levy, some parameterization of stable distribution. You have the Cauchy. Cauchy could be student T parameterized or the stable distribution parameterized. You have these distributions. Okay, so Give me a second to erase the board, and let's forget about this. If it's too technical for you, forget about it, because power laws are very intuitive, very easy to understand. Okay. Let me show you what happens with the Gaussian when you have decline. Probability of exceeding 3 sigma, 3 standard deviation, or 3 whatever, okay, is 1 in 740 times. Probability of exceeding 4 is 1 in 32k times. Probability of exceeding 5 sigma, 1 in 3.5 million. Probability of exceeding 6 sigmas, 1 in 1 billion. You see, what do you notice is acceleration of decline. But there is one central attribute to this. It's as follows. The ratio of 3 sigmas to 6 sigmas, you see, is going to be much, 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 much bigger than 5 sigmas to 10 sigma. 10 sigma is 1 in, I don't know, 13 to the 10 something. So as you go higher with a Gaussian, that ratio becomes different. With the power law, you don't have that. You have a constant ratio. The 2 sigmas divided by 4 sigmas, or $2 divided by $4, or $2 billion is the same as if you take another ratio, 5 divided by 10. It's the same probability ratio. Let's say I tell you how many people are richer than, okay? And I take 1 million, 1 in 62.5 people. Okay, let's assume, I know maybe not wrong, maybe soon with hyperinflation, it'll be 100% of the people or 99% of the people, but let's assume that work. Say richer than 2 million, 1 in 250. Richer than 4 million, 1 in 1,000. So you know automatically we're going to have richer than 8 million, it's 1 in 4,000. You double that number, you multiply by 4. The answer is very simply. That's what a power law makes things very easy. And you can predict. And incidentally, this distribution here does not have a variance, but you can understand it perfectly. You can even make it simpler, say with a stiffer power law, one that corresponds more to what we have in real life. Richer than 1 million, say, I'll start with 62.5, 1 in 125, 1 in 250, 1 in 500. There's a steeper power law. This one does not have a mean. Guess what? We understand, we know how it works. It doesn't have a mean, but you know, we can work with it, we can live with it. So the way we're going to simplify again the characterized power laws. Is as follows. Probability of exceeding x over probability of exceeding n times x. So here we use 2 times x before in the example. For a Gaussian or a Gaussian Bayesian depends on n and x. Depends on n and depends on x. For a power law, depends only on n. You don't care where x is. Let me give you another example with a Gaussian. Okay. The probability the probability, this is x, sorry, x, 2x, and a ratio. When x is 1, 2 sigma over 1 sigma is about 7. 4 sigma over 2 sigma is about 718. 4 sigma over 8 sigma is something of the order of 1010. So it increases. For a power law, depending how parameterized, you see, the ratio 4 sigma 2 sigma four times, we saw earlier, 4 times, 4 times. It's invariant. This is what we call scale invariance of the power law distribution. Tells you the following. The ratio of millionaires, so 2 billion over half millionaires is the same as ratio of billionaires over half millionaires, approximately. It's not going to be perfect. And sometimes this only holds for X large. Like if you take salaries, you will not find, or income, you will not find that property, you know, at the bottom, but you'll find that property high up. Now, for Gaussian variables, you don't have that property. The ratio of people who are, 3 meters tall over 1.5 meters tall is not the same as the ratio of 6 meters. There's no 6 meter, but you see, because of the rapidity of decline. So you can apply this sales of companies, stuff like that. This is the mark of a power law. I'm not going to go much further because I've written a lot on it. But now let's talk about Lindy in the 3 classes of distribution. Now let me discuss Lindy in that context. Let's talk about the Gaussian properties of Gaussian, which is what I call conditional expectation E of X, conditional X higher than K. Okay? And let's take this example, life expectancy. What is the expected life expectancy was X higher than 0. Let's say it's 80 years. Okay? Let's say now, what is life expectancy of conditional on being 80 years or older? Okay, you reach 80 years. What's the life expectancy? It's going to be 92. So in other words, an extra 12 plus 12. Okay? Actually, if you're healthy, much more than 92, incidentally. If you lift weight, if you don't hang around economists, if you don't read the right things, if you don't own Bitcoin, you live long, or the bad Bitcoin. All right. So let's say, what is life expectancy of X conditional X higher than 100? It's going to be, say, 102 and a half plus 2.5 years. So as you see, the extra life expectancy shrinks for things in the Gaussian domain. And then, of course, what is the life expectancy assuming X is higher than 120? Well, he just died for a second, right? In other words, when X, X, so when K goes up, okay, the life expectancy goes to K. You see? So that's the problem of the Gaussian. If I tell you what is the average deviation higher than 10 sigma, it is 10 sigma. Now for power law, you don't have this property. Okay? So we keep this, and let's say now we're increasing numbers. Okay? Typically for a power law, what is the expectancy? Let's say we start here with expectancy of X higher than 0. It's going to be 10. Now X, we increase, okay, X equal 10, maybe 20. It's a multiple of 10. Now higher than 20, 40. higher than 40, 80. And effectively, you see that, what is the ratio here is 2 times. You can see 1.5 times. See that, what's the average size of a company higher than $1 billion? It's 1.5 billion. No, sorry, it's 2 billion or something like that. Well, it's a constant. What's the average market move more than 2 sigma? This is 3 sigmas. More than 5 sigmas? 7.5 sigmas, whatever, however you define sigma. This is what's interesting, is that they're invariant. So this is the power law. Behavior is that it produces an expectation that is a multiple of that threshold. Okay. People grasp it when I present it that way. When I tell them if a technology is older than 10 years, it's going to be 20 years. Older than 20 years, maybe 40 years. It has to be a multiple higher. Now, when we talk about sub-exponential class, but not power law, that intermediate class, guess what? This is a constant. Some people say the crocodile has almost that. Whenever you spot a crocodile, say it has 20 years to live. If it's 10 years old, it has 20 years to live. If it's 20 years old, it has 20 more years to live. It's like what we call Poisson arrival. If things only die from shock, there's no aging. There may be a Poisson arrival in that class, the exponential class. So the borderline, which is sub-exponential but not power law, has this property. Okay, the exponential class having constant life expectancy. If the life expectancy is distributed according to this. And you see it in a lot of things where you may have a combination. To give an example, there was a paper recently and actually generated a debate that found that humans have visibly some decay because the mortality rate increases with time, that there is aging. But once you reach a certain age, it becomes 50% a year. So no matter how old the person is, whether 110 or 120, the person would have say 2.5 more years to go, regardless. So it becomes flat, means there's no more aging. And that produces completely different distribution of humans. It means that human life is unlimited, but short. That's what the title of the book was, the paper was. It generated some debates because some people weren't happy with the data. But the argument can be used for things in nature that we see are very old, like turtles and stuff like that. That maybe they're not immortal. You're never immortal because their accidents would kill you, but these accidents are memoryless. They're Poisson distributed. With Poisson distributed shock, you get this life expectancy. So I have very rapidly explained the power laws, the difference between these. Let me get a little more mathematical now. Let's say the probability exceeding x for power law is going to be something like, or converge for x very large, x, some constant, times x to the minus alpha, okay, for x very large. So you find this property that some people use something complicated you see in my book, the slowly moving function, and which tells you that log of x, if I take log of probability of exceeding x, if I take them log, it's going to be minus alpha log of something. So mathematically, we can express power laws as follows. A power law is for the tail, not the whole probability distribution. The probability of exceeding x, for x very large, is going to be approximated some constant times x to the minus alpha. Okay? So let's forget about what's in front of this, some scaling parameter, but that's the property of power law. Now, if I take the log of exceedance probability or survival function, however you want to call it, is going to be minus alpha, approximately, of course, plus something, log of x. And this equation is a central one that allows us, it comes from scalability, okay? Whenever you see log, you know that it's scalable. So it gives us the following. Take a log-log plot, log of x, log of probability exceeding x. You're going to have some, whatever, something like this. And then it becomes a constant with slope alpha. So typically, that's how we identify if it's power law. Sometimes it falls here because you don't have enough observation. You don't, by definition, you don't have a lot in the tails. Okay? And that alpha, the lower the alpha, alpha equal 1, you have Cauchy. Okay? The lower the alpha, the fatter the tails. And the higher the alpha, say alpha equals 3, we get something like the S&P 500, so between 2.5 and 3. The returns, not the price, okay? Something like alpha equals 2, you got earthquakes. Size of cities, somewhere between 1 and 2. The Gaussian, it becomes vertical. So alpha is effectively, that tail alpha is effectively infinite for the Gaussian. One property you need to note is that when alpha equals 1, no mean. When alpha equals 2 or lower, okay, no variance. When alpha equals 4 or lower, no kurtosis or infinite, depends on whether the moment is odd or even. But this is crazy because it tells you we can do statistics, we can understand everything, but the notions like variance, kurtosis, and even mean don't have any more meaning. But yet we can do, as I showed you, we can figure out the properties, we can work with wealth, we can work with probability. But the traditional notions that we saw in the beginning just do not apply. Let me stop here because I don't want to get too mathematical. I'd be mathematical in something where I can relax and express things in math in an uninhibited way. The math is incidentally in my book on fat tails. The whole book is about statistical consequences of fat tails, but most of it is about characterization of fat tails, the different classes, different colors, if you want, of fat tails. And this one I called alpha equals 1 or lower. I called the forget about it. It was spelled the way you should be pronouncing it, because you can't do traditional statistics at all. There's no mean, but sometimes you have the illusion that there is a mean. So thanks a lot for attending this lecture. Remember, this is a central lecture. Central lecture from this intuition, we can go very, very far in redoing statistical inference and redoing redesigning our views of the world on a more empirical basis and of course more solid mathematical basis. Thank you and have a great day.